Okay, so this is the last lecture of the basic cosmology series, and I wanted to discuss a little bit about the growth of structure. So until now, we have been mostly focused on the what is called the smooth universe or homogeneous and isotropic universe. And I have repeatedly mentioned that this is not the exact situation. It is not the real situation in the universe because there are inhomogeneities and anisotropies. And just to remind you, these are visualized here. Okay, these are pictures that we have seen before. The anisotropies in the cosmic microwave background temperature field in the sky on the left, and image of the local universe at very large scales, this time taken from the Sloan Digital Sky Survey, SDSS. Okay, and you can see that you use Hubble's law to convert redshifts into distances, and this is the image of the cosmic web. And we have been trying to understand how things go from early times to late times. So today, in this last lecture, the goal is to try and understand specifically, if I start with initial conditions which are tiny fluctuations of a density field 400,000 years after the Big Bang, then 13.8 billion years after the Big Bang, how come this structure emerges? So what are the physical concepts that go into this evolution? So here is a image or a movie from a simulation of the kind of physics we think is at play. And this physics is actually very simple. It is just Newtonian gravity at these scales. Of course, we have been discussing everything in the context of general relativity, but as you know, the small scale limit of GR is Newtonian dynamics. And as it turns out, that at the scales of interest in cosmology, once you achieve, once you reach late times, it is basically Newtonian gravity which is at play. At earlier times, this is not the case, and in fact, I will show you how GR and perturbation theory lead you to a situation where eventually you are at scales where Newtonian gravity is the only thing you care about. Okay, so you start with relativistic perturbation theory, and then you go into the nonlinear Newtonian regime. So this particular simulation, for example, was performed here. It is run using a publicly available code written by Volker Springel. It's called Gadget 2. You can download it from here. And these simulations are now not very difficult to do on a reasonable size cluster. And in fact, a lower resolution version of such simulations can also be done just on your laptop with 3 or 4 CPUs. Okay, so we have now the tools available to really start asking detailed questions. That was the motivation of this thing, of this slide. And I will come back to these simulations towards the end of the talk. For now, all you need to take away is that the initial conditions look reasonably smooth with small fluctuations in density. So this is density, which is shown here, colored by the color bar on a logarithmic scale. And you can see how dynamically the cosmic web is emerging. Okay, so you can see the filamentary structure and the dense regions where eventually galaxies will form, and these underdense regions which look like those empty regions from the survey that I was showing you earlier, and so on. All right, so this is a picture of a simulated universe. So let's start talking about the basic ideas underlying these notions of structure formation. So this is a brief outline of this talk. I will speak about length scales and why length scales and how they evolve is an important thing to consider. Because once you understand how length scales, different length scales evolve in the universe, then it becomes easy to understand and predict various aspects of the cosmic web. I will talk a little bit about the linear regime. Linear as in the equations of motion that we are talking about are nonlinear. But if we are dealing with small perturbations around FLRW, then those nonlinearities can be expanded in a Taylor series. And then you can say that I will keep only the first order terms, the linear terms of this Taylor series, and solve the equations in that regime. And that is called the linear regime. And then later, we'll see that as gravity starts becoming more and more predominant on small scales, rather, gravity is always there. The fact that overdensities become stronger and stronger will make you realize that the linear regime is no longer sufficient to describe your evolution, and that is the nonlinear regime then, where the full equations need to be treated in some way. And what we'll do is to discuss a couple of approximate techniques in which you invoke some kind of symmetry or other analytical approximation to try and get a pen and paper feel for what the answer should be. None of these are, of course, the exact answer. So for the exact answer, you have to run computer simulation. So like the one that I was showing you, and we will discuss this as well. All right. So this is a plot which is worth spending some time on, maybe like 5 or 10 minutes on, because it understanding this plot is what will then allow you to proceed in figuring out how structure formation occurs and why certain variables behave the way they do. So what is done here is on the vertical axis, I am plotting the logarithm of a length scale, of a physical length scale, okay, a proper length scale. On the horizontal axis, I'm plotting a unit of time, in this case, the log of the scale factor. Okay, and remember that the scale factor in an expanding universe is a good clock to use because it is monotonically increasing with cosmic time. So I might as well use the scale factor as a clock. And if I take the log of the scale factor, I still get a monotonically increasing quantity. So I can use log A as my time. So time is increasing to the right on this plot. And I have length scale, which I want to plot here. Okay. So let's start with the red line. And in the red line, and I'm using units in which C is 1. So this is the Hubble radius, okay, C over H. And I have plotted the Hubble radius as a function of time. It's a qualitative plot, so I'm not going to bother putting values on the vertical axis, but the qualitative behavior will be important to follow. So consider the period of inflation, which we discussed in the last lecture. As I had argued there, inflation is a period of this exponential expansion, and typically one achieves this using a slowly rolling scalar field, which dominates the expansion of the universe and behaves almost like a cosmological constant term, not quite. But for all practical purposes, because the Friedman equation is dominated by a cosmological constant term, the Hubble expansion parameter is almost a constant. Therefore, the Hubble radius, which is C by H, is approximately a constant in this phase. Okay, so this is the inflationary phase. Now, this is a cartoon picture, so I'm not going to show you details of how reheating, etc., happened, but something happened and inflation ended. And soon after it ended, a radiation dominated phase began. Okay, this is the idea of having inflation in the first place, that you want to then go into a standard cosmological expansion dominated by initially by radiation. So during radiation domination, if you remember the scale factor, so radiation domination means that the Friedman equation h squared is equal to an energy density, and the only energy density is radiation by assumption. Radiation falls like 1 over a to the power 4. So h falls like 1 over a squared. So h inverse increases like a squared. Okay, so on a log-log plot, if I plot 1 over h during radiation domination, it will be a straight line with slope equal to 2, plus 2. So that is what I've plotted here. Then eventually, as you remember, if there is also non-relativistic matter, like cold dark matter, for example, or also baryons, then because the non-relativistic matter energy density is falling like 1 over a cube, while radiation is decaying like 1 over a to the power 4, eventually these two energy densities will become equal, and sometime after that, it will be the matter energy density which will start dominating. So in this cartoon picture, let's assume that the radiation matter equality epoch occurs here. And then after that, the Friedman equation gets sourced only by non-relativistic matter. So h squared becomes proportional to 1 over a cubed, because non-relativistic matter falls like 1 over a cubed in its energy density. So h goes like 1 over a to the 3 halves. And therefore, h inverse goes like a to the power 3 halves. So then in a log-log plot, I will get a straight line which has a slope of 1.5. So it is smaller than 2. Therefore, this line is less steep than this part of the line, but it is still a line which is greater than slope greater than 1. So good. This is the behavior of the Hubble radius as a function of time in inflation and in the post-inflationary epoch with radiation and matter. Now, what is shown in the dashed lines are three different example choices of fixed co-moving length scales. Okay, so I pick a co-moving length scale lambda 1. or well, okay, lambda 1 is the physical length scale. But I pick one co-moving length scale, co-moving length scale number 1. I pick a second co-moving length scale which is smaller than the first one. So let's say the first one is 100 MPC. Or wait, so let's see. So the first one, let's make it, yes, 100 MPC is fine. The second one, let's make it around 50 MPC. And the third one, let's make it around 5 MPC. Okay, so that's why the first one is sitting on top, the second one is below it, and the third one is even below. What is shown in the dashed curves is the evolution of the corresponding proper length scale. Okay, so my co-moving length scale is fixed to 100, 50, and 5 MPC. But my proper length scales, remember, will be proportional to the scale factor always, right? Each of them is proportional to the scale factor. So on a log-log plot, each of these lines will be straight lines with slope equal to 1. And they will be ordered like this because of my choice of length scales that I have decided to show you. So now, if you think about what I just said, so here H inverse is a constant. So these lines are, of course, all increasing faster than H inverse. Then here, in this epoch, H inverse increases with slope 2, and here it increases with slope 1.5. And all these curves, the blue dashed lines, are increasing with slope 1. So in all of this regime, their slopes are smaller than the slope of the corresponding Hubble radius. So that leads to this very interesting behavior. For example, this 100 MPC curve that we plotted here, at these time scales which I'm showing here. Okay, so in this part of the image, this curve it has a value which is smaller than the Hubble radius. Okay, so the proper length scale that you're talking about has a value smaller than the Hubble radius. In this regime, perturbation theory will tell you that the amplitude of a perturbation whose wavelength is given by this particular wavelength is allowed to increase with time. Okay, it is allowed to grow. It is allowed to gravitate. Here, something interesting happens. At this epoch, this particular length scale has a physical or proper value which is equal to the Hubble radius. And after that, it becomes larger than the Hubble radius because the blue dashed line is above the red line here. So perturbation theory now tells you that if I have a Fourier mode, for example, whose wavelength is longer than the Hubble radius, then the equations of motion do not allow the amplitude of this Fourier mode to increase as a function of time. The amplitude of this Fourier mode freezes in time. Okay, this is something that comes from perturbation theory. And it is not difficult to understand. It's basically saying that my wavelength is so large that my local causality is preventing me from sending signals quickly to, in order to make this wavelength perturbation increase. Because if I have a wave which is supposed to be part of my description of the growing inhomogeneities, this wave can only increase by changing its amplitude. Okay, but increasing the amplitude of a wave means increasing the value of density at one point and coherently decreasing the value of density half a wavelength away, and then coherently increasing it again a full wavelength away, and so on and so forth. So if my wavelength is very, very long, then causality will prevent this kind of information to be passed over very long distances. So it is not surprising that the long wavelength, the wavelengths which are longer than the local causal horizon, which is the local Hubble radius, these are not allowed. So that remains the situation for this particular wavelength mode all the way out here. And interestingly, at a time when inflation ends, this wavelength mode still has a wavelength which is larger than the red curve, right? Because here, this blue curve is above the red curve. And in fact, even when you enter the ordinary expansion of the universe, which is radiation dominated, for a long time, this particular wavelength mode, we gave an example of a 100 MPC mode. This wavelength mode remains above the red line for a long time. In fact, in this example, it even remains above the red curve at the time of radiation matter equality. And only deep in the matter dominated regime does its value become equal to and eventually smaller than the Hubble radius. Okay, so it crosses back in and then becomes smaller than the Hubble radius, and then it stays here. And then we are not discussing what happens in the future, but right now we only want to understand what happens around these epochs. So for all these epochs, Fourier mode, which has a wavelength given by this particular value, will have its amplitude frozen in time, and then at some point during matter domination, its wavelength will become smaller than the Hubble radius, and then its amplitude can again grow through the equations of gravity. Okay, so all right, so this is the issue here. On the other extreme, look at this 5 MPC mode, 5 or whatever small scale mode. In this case, here the 100 MPC mode had become larger than the wavelength had become larger than the Hubble radius at some early time during inflation. This 5 MPC mode has to wait for some more time before its wavelength becomes larger than the Hubble radius. Okay, but it does become larger. And then just the geometry of this picture tells you that this particular mode, because it exited the Hubble radius, this is the jargon that is used, this mode exited the Hubble radius here, this one exited here. And this geometry is showing you in this image that the mode which exited later will also enter the Hubble radius at an earlier time compared to this other one. Okay, so this crossover from being larger than the Hubble radius to smaller than the Hubble radius is like saying I have become, I have come inside a patch of Hubble radius size. So I have entered the Hubble radius. And here I became larger than the Hubble radius patch, so I exited the Hubble radius. So this Hubble radius exit and entry are in this particular way for this small scale mode. And the interesting thing here is that this small scale mode has entered the Hubble radius during an epoch when the universe was radiation dominant, right? Because this is when the slope is 2. And this large scale mode entered the Hubble radius during matter domination. And then by extrapolation or interpolation between these two, you can argue that there must be a mode which is exiting the Hubble radius somewhere in between these two and entering the Hubble radius again roughly exactly around the time when radiation matter equality happens. Okay, so this is, of course, it has to be the case by continuity. So this is the situation for these modes. And now the physics is very interesting for this mode and the in-between modes. Okay, so it is interestingly different for these modes. The reason is that these modes, when they enter the Hubble radius and are susceptible to gravitational growth, the universe is radiation dominated, as opposed to the universe here when these modes are entering where the background is matter dominated. Okay, so basically what happens is during matter domination, essentially ordinary gravity plays a role, and it's like gravitational attraction in the usual sense, and an overdense region will very quickly start becoming more and more overdense. So all the modes which enter here during matter domination will, as soon as they enter, they will start gravitating in a more or less normal fashion. These modes which enter during radiation domination are very interesting because the presence of radiation and fluctuations in the radiation prevents these modes from growing very quickly. Okay, and this creates a difference at late times between these modes. Because, for example, now suppose the end of these curves corresponds to current epoch. Then at current epoch, I can ask the question, what is the amplitude of this Fourier mode? What is the amplitude of this Fourier mode? What is the amplitude of this Fourier mode? Each one of them. Okay, starting with some initial conditions. And what you can show is that in relative terms, the amplitude of these Fourier modes will be different from the amplitude of these Fourier modes. Okay, so the amplitude of the gravitational potential, for example, will be very different. Here, the gravitational potential would have been allowed to stay constant or even slightly increase, etc. Typically stay constant. The gravitational potential here would have actually decayed because the presence of radiation fluctuations and just the background radiation being what it is would not have allowed perturbations to grow very rapidly. Okay, so I don't know how much you have absorbed from this discussion, but the bottom line takeaway message is that different kinds of physics are at play at different length scales and at different epochs in the universe. Okay, so by epoch, one means is the universe radiation dominated or matter dominated? By length scales, one means are you a large length scale or are you a small length scale compared to the length scale which entered the Hubble radius at the epoch of matter radiation equality. Okay, so if you're larger than that length scale, you will enter during during matter domination, If you're smaller than that length scale, you will enter during radiation domination, and the physics that you will be susceptible to will be very different during these epochs. Okay, so this is like a very hand-waving qualitative picture. So let's put in some numbers to this. So we are starting with a very early epoch. Let's say you pick an epoch around redshift of 1100, which is well after the So observationally, why do we expect that small perturbations are a valid way of proceeding? It's because at least at t equal to 400,000 years after the Big Bang, we know that baryonic perturbations were at the level of 10 to the minus 5, and cold dark matter perturbations were at the level of 10 to the minus 3. They are 100 times different from each other, but both of these numbers are very small compared to 1. So small fluctuations is a very good approximation, at least at this epoch. And by extrapolation, if our theory of the universe is correct, then even at earlier epochs, you should not expect large fluctuations. In fact, you would have expected fluctuations to be even smaller before. Okay, so this is the motivation behind trying to use this kind of picture to explain how perturbations grow. So let's put in some equations as to what one means by the growth of, like what one is trying to solve when you want to study the growth of fluctuations. So to keep things simple, I will not discuss baryonic and radiation perturbations here and only focus on the perturbations of cold dark matter because they're simpler to handle. Okay, and similar things you can do for baryons and radiation, and Dodelson's book is an excellent place to look at this. So focusing on CDM, if I say that the universe is almost homogeneous and isotropic with only tiny fluctuations, then what I can do is to take my tools from the FLRW universe, namely the metric and the energy momentum tensor, and introduce small fluctuations which are inhomogeneous on top of the homogeneous and isotropic background. So for the metric, this means that I can perturb the elements of the metric by introducing functions which like phi and psi here, which depend on space as well as time. So not only on time like the scale factor, but also on space. I've also chosen to write things in terms of a slightly different time variable. It's called conformal time instead of cosmic time, but that's not it's just a technical issue. Okay. Then at the level of the energy momentum tensor, earlier I had a diagonal energy momentum tensor, and basically it was a pressureless matter if I look at cold dark matter. So I only had T00 to be non-zero. Now I will have T00 to be some non-zero quantity which can depend on space through this function delta. And I can also have off-diagonal terms and pressure-like terms. Okay, these pressure-like terms are actually related to velocity dispersion and bulk velocity flows. And the off-diagonal terms are also related to bulk velocity flows. Okay, so my energy momentum tensor can be written in this way. And what I am saying now is that the new variables that I have introduced are these quantities phi, psi, delta, and v. Okay, and phi and psi will be very similar to each other. In fact, in the standard models, they are equal to each other. In non-standard models, they can be different. And delta and v are again small perturbations. Physically, the interpretation is that this phi and psi are like the Newtonian potential. Delta is the over density of dark matter, over density or under density. It's called the density contrast. And v is like a peculiar velocity, peculiar in the sense that your fluid elements, which used to be on constant coordinates in the homogeneous and isotropic universe, if you ask for geodesics of the FLRW spacetime, these would be x equal to constant, y equal to constant, z equal to constant. So now the fluid elements on geodesics no longer hold x, y, z to be constant. They move with some local velocity relative to this XYZ reference plane. Okay, so that is this peculiar velocity here. And the entire idea of perturbation theory is that delta, v by c, and psi by c squared, these are all dimensionless quantities, and they are all expected to be of the order of some small control variable epsilon. You can think of epsilon as the control variable which sets this number 10 to the minus 5 or 10 to the minus 3 here. Okay, so that is the way the calculation is organized. So if I take this metric and this energy momentum tensor and I plug it into Einstein's equations or the matter energy momentum conservation equations, what I will get is this system of equations. I get an equation which looks very much like the Poisson equation, except I have a couple more terms which are relativistic in nature. They come from the fact that you're not doing Newtonian dynamics, we're actually solving GR. Then I have the continuity equation, which looks very much like the usual fluid dynamics continuity equation, modified again by a relativistic term. And I have the Euler equation, which basically is the same as the usual Euler equation, except that there is a Hubble expansion term here. And then there are higher order terms in all of these, which I have chosen to ignore. Okay, so it turns out that these equations, even if you want to study beyond linear effects, these equations are a pretty good approximation for CDM perturbations. Formally, you can also derive the continuity and Euler equations from the collisionless Boltzmann equation. So this gives you a connection to statistical mechanics, where I can ask for the evolution of the distribution function of dark matter, which is given by the collisionless Boltzmann equation, and taking moments of this Boltzmann equation with respect to velocity will give me the continuity and the Euler equations. The zeroth and the first moments will respectively give me these equations. Okay, so these are the equations governing the CDM perturbations, and now you can plug them into a computer or do analytical calculations and solve them. And again, Dorelson's book is a good place to look at the discussion of how these things are solved. I have stolen the next couple of plots from chapter 7 of that book. And what one finds is that if I follow the evolution of the gravitational potential in Fourier space, because I can, if I linearize these equations, for example, look at the Poisson-like equation here, all the appearances of psi and delta are linear. Okay, and I'm operating on this with a time derivative or spatial derivatives or nothing. So I can take a Fourier transform very straightforwardly. Here I will get a k squared term, here I'll get a time derivative, here I'll get nothing. And then the Fourier modes are what I'm solving for. And similarly, if I linearize the continuity and Euler equations, I will throw away the nonlinear terms like this one, the V grad V term, and I'll throw away the delta times V term. And what will be left is a set of linear equations, and I can again Fourier transform those. And then once I have Fourier transformed, I have an ordinary set of differential equations coupled to each other and linear. And these are completely straightforward to solve, especially if you put them on a computer. And they are also not very difficult to solve analytically. Okay, so you can do this and then ask, how does the gravitational potential behave as a function of time? And that is what is shown here. And in the next slide, I'll show you how the density contrast of dark matter delta behaves as a function of time. Okay, so for now, let's focus on the gravitational potential for different Fourier modes. So remember, Fourier modes are labeled by the value of the wave number k. Wave number is inverse of a wavelength. So I gave you all this long explanation of how wavelengths behave relative to Hubble radius. And now you have to just do 1 over all of that in order to understand how I gave you an explanation of how wavelengths behave, right? Now we want to understand how wave numbers behave, okay, modes with different wave numbers. So all you have to remember is that if I give you a small value of k, it means it's a large value of wavelength because 1 over k is large. Similarly, if I give you a large value of k, like 2 compared to 0.01, then this corresponds to a small wave. So these long wavelengths, remember, are the wavelengths which entered the Hubble radius at late epochs during matter domination. So I'm going back. These are the long wavelengths, okay, entry during matter domination. Small wavelengths, short wavelengths, entry during radiation domination. So let's go back here. Here is the solution of a gravitational potential for a Fourier mode with a long wavelength. And the solid part of this curve corresponds to the epochs when the wavelength is outside the Hubble radius. Okay, and so you can see that from solid, this curve becomes dashed at this point, and that is well after the radiation matter equality epoch, which is marked by this vertical line here. So this mode, as you can see, the Fourier amplitude of the gravitational potential is not changing much. It slowly decays a little bit, but more or less it's frozen at its value within 10% or so. And this is a mode which remained outside the Hubble radius for most of the interesting history of the universe. Only at this very late epoch in matter domination, it has entered the Hubble radius. And it so happens that for this particular solution, even after entry, the value of this mode remains constant in terms of the gravitational potential. Again, density contrast of dark matter we will see in the next. So contrast this behavior of this particular mode with the behavior of this mode, which is a mode corresponding to a very short wavelength. And you can see that this mode is already a dashed line, which means this particular wavelength entered the Hubble radius already before you can see even what is happening here. Okay, so at very early epoch, deep in the radiation dominated region. And what you can see is dramatically different from what happens here. This mode, after a certain amount of time during radiation domination, it falls very rapidly, rapidly decays, and then starts oscillating about a value which is very close to zero. And then it remains at constant at this value at late times once matter domination kicks in. Okay, so this is qualitatively very different from this long wavelength. And in between, there is this mode which enters more or less a little bit before the radiation matter equality. I mean, you could have also tried to show a mode which enters exactly here, but such a mode has not been shown here. A different mode has been shown. It is still useful to see its evolution. Here also, it has entered during radiation domination. It has decayed, but it has not decayed as much as this guy. Okay, this guy entered even earlier during radiation domination and decayed a lot. This one entered closer to the radiation matter equality and decayed a little bit. And then it also tried to oscillate somewhat, not as much as this one, but a little bit. And then it flattened out at a non-zero value, which is higher than the one for the short wavelength. Okay, so this picture already gives you a feeling for what different kinds of modes are going to do in terms of their gravitational potential, the value of the gravitational potential. Okay, so in terms of the density contrast of dark matter fluctuations, the situation is a bit different. Basically, dark matter is gravitating, so you expect its density contrast to increase as a function of time. And in fact, this is what happens. The same kind of modes are shown, not exactly the same values, but very similar. And now what you see is that the small scale mode, it increased in time during radiation domination, but it increased relatively slowly compared to what it's going to do during matter domination. Okay, so here it was increasing by some amount. It did some strange things here, and then it settled into a growth, which is a very steady power law like growth during matter domination. So this is a small scale mode. Correspondingly, a large scale mode remained basically frozen for a long time. And then eventually, once it entered the Hubble radius deep during matter domination, then it went into this steady kind of growing power law kind of. And again, the intermediate mode did something in between. So the growth of the density contrast, especially when you are in the matter dominated regime, which is at late times, and when you are substantially below the Hubble radius in terms of your wave number, such epochs and wavelengths for the density contrast can be handled completely analytically because the equation governing them becomes independent of the wave number. Okay, so you can show that the density contrast, you basically combine the continuity, the Poisson, and the Euler equations, and you can derive a second order ordinary differential equation for the growth of delta for all the modes which are sub-Hubble, as in their wave numbers are below the Hubble radius. Okay, and that equation is given here, and you can solve this very easily. For example, if I do this during matter domination, the equation becomes very simple, and the solutions to this equation can be just written in terms of power laws as a function of A, and you can easily check just in your mind also just now that delta proportional to A, just A to the power 1, is a solution of this equation. Okay, so there is a growing mode of this equation which is growing proportionally to the scale factor. There is also a corresponding decaying mode to this equation which decays like 1 over 3/2 power of the scale factor. Okay, so just to tell you that the behavior of small scale perturbations or sub-Hubble perturbations, they may be small or large in absolute terms, but they have to be sub-Hubble. This behavior is analytically very well understood. And it is captured by the solution of this equation, and the solution is called as D1, it's called the growth function. Okay, and this quantity T of K here tells you the relative amplitude of these modes at a time when you can use this equation. And this relative amplitude is basically set by these kind of considerations because long wavelength modes have a gravitational potential which remains quite high. short wavelength modes have again a constant gravitational potential, but with an amplitude which is very low. Okay, so this relative change in the amplitude of the gravitational potential is captured by what is called a transfer function T of k. So the linear perturbation theory regime is very well described for dark matter fluctuations by this solution, which you see written down in front of you. Okay. So now what I can do is calculate the statistics for this kind of evolving universe in the linear regime. And I can ask for the 2-point function of this Gaussian random field that I had discussed earlier. Okay, and this theory will tell you, starting from some initial conditions, how will the Gaussian random field evolve. And you can see that already here in terms of time evolution, the power spectrum of this field will grow like d squared, d1 squared. And the k dependence will be basically determined by the square of this quantity. And this phi primordial, the square of this quantity, is basically the same as that p zeta of k from the previous lecture. Okay, it is determined by inflation. This is the primordial power spectrum laid down by inflation. And then the square of this transfer function will additionally give you modifications due to what happened to different modes as they entered the Hubble radius, either during radiation domination or during matter domination. Okay, so that is the way this calculation is organized. And what you find at the end of the day for the so-called matter power spectrum is this very characteristic shape that at very long wavelengths or small values of k, the power spectrum is basically determined by whatever the primordial power spectrum is. Okay, so nothing has changed here compared to primordial power. The only thing that might have happened, this is in terms of the shape of the power spectrum, okay, the k dependence. In terms of the time evolution, of course, there is this b squared, which is changing the amplitude, but only the amplitude has changed here. The shape has not changed. At very small scales or large values of k, this decay of the gravitational potential has played a role because the transfer function T of k at these large values of k has become very small. Okay, and that is what you see here. This is basically the behavior of this p squared of k, which is a falling function of k. So this corresponds to the modes which entered during radiation domination, and their growth was basically was arrested. And in between, there is therefore a peak, because here the primordial power tells you that I should increase as a function of k. Here, the radiation dominated or radiation affected modes tell you that power should decrease as a function of k. And by continuity, in the middle, there should be a peak. The location of this peak is closely connected to the radiation matter equality epoch, basically which length scale crossed the Hubble radius during radiation matter equality. But the value of the radiation matter equality epoch, and therefore of the length scale which crossed at that epoch, is determined by the cosmological parameters omega matter and omega radiation, and also the Hubble parameter. That means that the location of this peak is actually a cosmological probe, because if I can measure the power spectrum in data using some tracer, and I see this turnover, then that directly gives me a measurement of a combination of cosmological parameters. And this was recognized early on, and there were surveys set up to try to look for this turnover. Turns out that these length scales are actually quite large. They are 100 MPC or so, which means getting accurate statistics, which will be able to show you this turnover with very small noise. It requires volumes that are substantially larger than 100 MPC scales. Okay, so imagine that this is a 100 MPC sized ruler, and now you want several of these rulers to sit inside your volume so that you build up enough numbers to be able to measure this correlation or this 2-point function in an accurate way. And it took a long time for surveys to come to this stage. Now surveys are approaching the stage where this turnover scale is being approached. Okay, so this is a tough measurement to do, but the power spectrum itself of galaxies, for example, is now a reasonably routine thing that is measured in large volume surveys. Okay, so this is as far as the power spectrum of linear theory is concerned in cold dark matter cosmologies. I just wanted to show you a slightly different way of looking at the power spectrum. You can non-dimensionalize it. So if you go back to the definition of the power spectrum and you look at the definition of the Fourier transform, remember delta k is like an integral over volume of delta of x. delta of x is a dimensionless quantity because the way delta of x is defined is in terms of number relative to unit. Okay, so delta x is dimensionless. So if delta x is dimensionless and delta k is a volume integral of delta x, then delta k has units of volume. So now if I take two powers of delta x, of delta k, on the left hand side I have units of volume squared. The Dirac delta in three dimensions in k space also has units of 1 over k cube, which is like a volume. Okay, so in order to balance the dimensions, my p of k must have units of volume. So that's why you can see that this p of k is measured in measured in MPC cube units. So if I want to be a little more, abstract, what I can say is that let's non-dimensionalize the power spectrum. I'll multiply to the power of k cube, therefore 1 over volume, so that this quantity is dimensionless. And this quantity capital delta squared, I can interpret in terms of the dimensionless power per logarithmic scale in k space. So what has been shown here is the square root of this delta squared as a function of k, and what you can see is the expected linear power spectrum for different kinds of dark matter models. So if dark matter is perfectly cold, which is a very theoretical and ideal kind of situation, then its power spectrum will look like this solid line. Basically, it will increase very rapidly, this non-dimensional power spectrum at low k, and then eventually it will increase only logarithmically. Okay, but if my dark matter is not perfectly cold, in fact, so for example, if I have a warm dark matter candidate in which there is a free streaming scale, then I start becoming sensitive to the location of this free streaming scale, because below the free streaming scale my perturbations will get wiped out. For the same reason, for example, that photons will tend to wipe out fluctuations, a relativistic particle will also tend to wipe out fluctuations below its free streaming scale. So here are examples of different kinds of these warm dark matter universes in which the mass of the warm dark matter is taken to be some different values. Again, as I decrease the mass, I go from a perfectly cold system to something which has a strong cutoff in its linear power spectrum. Okay, and this is the kind of thing that people are trying, one of the things that people are trying to constrain using observations of the small scale power spectrum of the universe. Okay. So that is as far as linear theory is concerned. And now in the remaining 15 minutes or so, I want to go a bit beyond linear theory and discuss nonlinear dynamics. Okay, it is going to be a very broad brush overview because this part you will see in much more detail in the structure formation lectures. So there are a few different analytical approximations that are available in order to go beyond the linear approximation. I'm just going back to those nonlinear equations. These are the equations we want to solve in their full nonlinear behavior. Okay, so the way they are written down here, I want to solve them. I can't do it analytically just like that. So, but I can try if I make some strong assumptions. So one strong assumption is that of spherical symmetry. Okay, so I assume that my initial perturbation is a spherically symmetric ball of dust sitting inside an overall homogeneous and isotropic universe. So the initial picture is shown here. It turns out that in such a situation, the only dynamical variable now becomes the value of the radius of this ball as a function of time. Because inside the ball, I have a homogeneous universe. Outside the ball also is a homogeneous universe. It's just that the density of these two homogeneous universes is different. So all I need to know is where is the boundary of these two universes. Okay, and the location of that boundary is given by this capital R as a function of t, and I can write down an equation governing the evolution of capital R. And it turns out, because of the way GR is structured, that this evolution equation looks very similar. In fact, it's identical to Newton's law. d2r by dt squared is minus g times mn closed divided by r squared. We know how to solve this equation. The solution is a cycloid. We do this in undergraduate physics, and the answer can be written in this parametric form. Okay, so r is a function of t, parameterized by this fiducial or this auxiliary parameter theta. So theta goes from 0 to pi, and basically it's describing evolution of overdensity whose radius increases as a function of time, turns around, and then collapses. This is actually also identical to the equations of the FLRW universe in the closed system, which Friedman had derived in 1922. Okay, and it's not surprising because what one is saying is that these two universes are different. The difference is that the outside is, let's say, a flat FLRW universe, and the inside is actually a closed FLRW universe. So it's called the separate universe picture for this kind of setup. So several things can be done. For example, I will only spend time on this one thing, where you can analytically write down the evolution of the enclosed density of this ball. Okay, and it turns out you can write it down completely analytically in this way. And what you see is that as theta goes from 0 to 2 pi, this density at late times, especially when theta is approaching 2 pi, cos theta is approaching 1. So this 1 minus cos theta is approaching 0. In the numerator, I have theta minus sine theta. So sine theta approaches 0, but theta approaches 2 pi. So the numerator is finite, the denominator is going to 0. So this model is a very idealized situation. Therefore, it is describing a density which is going to increase to infinity, or it may become a black hole at some point. Okay. So this is an idealized situation, and it is happening because your approximations are too strong. In a more realistic setting, you would expect that virialization might happen. Okay, so if I have random motions also available in the dust, which is forming this collapsing matter, then at some point virialization may happen, and then you can ask what happens to the stable structure that is formed after virialization, and this can also be calculated within this model. And what you find for example, is that the radius at which virialization occurs, its value is half of the turnaround radius. So this turnaround radius is the value of the radius at the location of turnaround, and half of that is where the virialization will happen, and then this curve will just smoothen out. Okay, so that is the kind of thing you do in this. This is called a spherical collapse model. You can look at Paddy's book. There is a whole chapter on doing this in great detail. Another kind of approximation, which is also very useful numerically, is the so-called Zeldovich approximation. This is even earlier than the spherical collapse approximation. In the Zeldovich approximation, what one argues is that let's assume that initial velocities that are given to fluid elements don't change in their direction. Okay. So initially, I have given some directions to these velocities determined by the gravitational potential and its derivatives. And I will just use linear theory to solve for the magnitude of the velocities of these fluid elements. Okay, so this f of t, which is the magnitude of the velocity, is determined by linear perturbation theory. It turns out to be basically equal to the time derivative of the linear theory growth factor, which we saw before. And the directions of these velocities and the remaining part of the magnitude will be set by the gradient of the initial gravitational potential at some early time. This is the Zeldovich approximation. It is also the first order in what is called Lagrangian perturbation theory. And in this approximation, fluid elements will basically travel in straight lines. And this is, of course, not correct because actually, when you have full gravity, two fluid elements which are approaching close to each other will start feeling each other's attraction, for example, and the directions of their motion will respond, right? They will go into some orbit. But in the Zeldovich approximation, this will not happen. They will just continue going along whatever path that had been chosen for them. And this is an approximate way of asking for the evolution of matter. So what is shown here is a video, a movie created by former IUCAA student Sujata Ramakrishnan. And what she did was to just put this on a computer and ask as a function of time what happens to these fluid elements. And what you can see, and this was also known, of course, for 30 years or so, is that just this very simple approximation, starting with a Gaussian random field, will very naturally produce a structure that ends up looking similar to the cosmic web that we are used to seeing in all these pictures of real data and in n-body simulations. Okay, so this is a very crude way of doing an n-body simulation. It also doesn't really work at very late times. But if you are careful about the scales that you're resolving and the time up to which you evolve the simulation, the result looks like this, which is in fact very, very similar to the nature of the cosmic web. Okay, so this is an interesting approximation to keep in mind. But finally, if you really want to look at things in detail, you have to solve these equations numerically. And the way one generally does this is using the n-body technique, which I will discuss in the next slide. And I just wanted to show in this slide that by now the technology of producing cosmological simulations is very advanced. There are also many publicly available simulations. So, for example, the simulations, some of them listed here, like Bolshoi and Multidart, they are publicly available. You go and Google them, and you will see. You can ask for access to the database that has been maintained by the people who ran these simulations, and you can download the data from here. You can make these kind of plots on your own, and you can you can step through the simulation. You can take a snapshot at a particular time and explore it in space, or you can take slices of the simulation volume at different times and explore things as a function of time. You can calculate various statistics, you can do visualizations, etc., etc. Okay, so if you're interested in this kind of thing, all of this data is publicly available. There are also publicly available analysis tools written in Python, for example. So if you know a little bit of Python, you can go and start using these tools as well to help you understand how the universe evolves, at least in these computer simulations. So what does one actually do when simulating cold dark matter? The goal is to solve the collisionless Boltzmann equation with cold initial conditions. Okay, so this is the theoretical setup which I was arguing before as well. You cannot do this very easily because the collisionless Boltzmann equation is an equation in 6 variables as a function of time. Okay, 3 position variables, 3 velocity variables as a function of time, and you want to solve for the distribution function. This cannot be done using these random initial conditions without assuming any symmetry, etc., even on the most powerful computers that we have today. So instead, what one does is to take a different approach where you say that instead of solving things on a grid, for example, in position and velocity space, I will solve the system statistically. So I will sample the initial distribution function statistically, and I'll create a set of numerical tracers of the distribution function. I'll call them particles. Okay? They're not real particles, they're just tracers of you can think of them as fluid elements of dark matter. These fluid elements will move as the distribution function evolves, okay, because they are tracing the shape of the distribution function. So using the collisionless Boltzmann equation, you can ask the question, how do the tracers of the distribution function evolve if the distribution function obeys the collisionless Boltzmann equation? Okay, you can map from one to the other. It turns out that the evolution of these tracers is essentially the same as the geodesic evolution of a set of particles acting under gravity in an expanding space. So that is what leads to this idea that instead of solving for the distribution function itself, let's put down a set of fake particles in a volume and let them obey standard Newton's law augmented by the Poisson equation for their motion and in expanding coordinates. So this is very straightforward to set up. And then the remaining stuff is mainly technical. Okay, so for example, these are not really billiard balls that are colliding with each other. So you should avoid two-body collision effects because they are supposed to be blobs of collisionless dark matter. So they should be allowed to pass through each other if they come close, or they should not be allowed to affect each other very strongly and go into hyperbolic orbits or something. So you have to modify Newton's law at small scales in the simulation artificially. And the way you do this will lead to some strange effects at small scales. So then you have to ignore the very small scale. So this sets a limit on the resolution in terms of length scale that your simulation can achieve. Then, for example, if you naively do particle counting for calculating your Newtonian forces between pairs of particles, this will be like an n-squared calculation, which will again take a long time. But you can use Fourier techniques and you can use tree techniques to beat down this n-squared scaling and bring it down to something like n log. Okay, and then finally, you have to also worry about the fact that you are sampling with a finite number of tracers in a finite volume. So you will have numerical effects related to the resolution that you can achieve. So if you had more number of tracers, you would do a better job. So then any statistic that you deal with, you have to ask the question, has this statistic converged with respect to the number of tracers that I have? Okay, and then also if with these other technicalities with respect to the small scale modifications of Newton's law, have I converged? With respect to the Fourier grid, have I converged, etc. So this is the way the state of the art has been developing. Computer simulations are already being run very, very early in the 1970s and 80s. They really came into their own in the 90s when people started using them for in cosmological volumes, and today they are run at very, very high resolution in very large volumes. Again, typically one puts a periodic cubic box in co-moving coordinates for simplicity mostly. And again, the periodicity of the box, you have to make sure that you're not sensitive. Okay, so for example, the results of a simulation can give you a wide variety of outputs. For example, you can identify virialized bound objects, which are called halos. You can identify substructure. You can see that substructure here. Here is a bound object. The whole thing is a gravitationally bound system, a dark matter halo. But inside, you can see clumps of high density at different places. Okay, and at the very center, there's a very, very dense clump. So this kind of hierarchy of clumps is a very natural prediction of the cold dark matter framework, and the simulation allows you to resolve this. And then you can ask for the distribution of these clumps or halos as a function of their mass. This is called the halo mass function. You can ask for the growth of these clumps as a function of time. So this is the accretion history of halos. You can ask for the statistics of the large scale distribution of these objects. This is the 2-point function or the power spectrum shown here for these halos. Okay, so these kind of things you can do, and now these simulations are becoming sophisticated enough that you can directly start comparing the simulations with observations using some techniques to map dark matter to galaxies, etc. Okay, and that is what is now allowing people to study cosmology using these kind of simulations as well as analytical techniques and semi-analytical tools. So this is all I had to say. I will stop here. It's the end of the series, so I'm happy to answer any questions, not only about this lecture, but also about anything else we have discussed. So there is something in the chat. Okay, in the linear regime, why does the matter that decays earlier oscillates more against gravitational potential? Very good catch. You have a very sharp eye. So this happens because the matter which, so the modes rather that enter during radiation domination, the universe is radiation dominant. Okay, so there are fluctuations in the radiation field as well. And it turns out when you go through the equations that these fluctuations in the radiation field, they tend to produce oscillatory solutions of the gravitational potential. So the deeper in the radiation domination epoch you enter, the more susceptible you are to these oscillations. And as you come closer and closer to matter domination, the amount of radiation is decreasing relative to the amount of matter. So the effect of these radiation perturbations becomes weaker and weaker, and therefore the effect of the oscillations also becomes weaker. And I should also mention, this has nothing to do with the baryon photon oscillations that we were talking about. Okay, so the solutions I was showing you were completely for dark matter and radiation during radiation domination, and with radiation perturbations also thrown. Okay, so there were no baryons in the picture. So the baryon acoustic oscillations are a completely different phenomenon. Yeah, so I hope that makes it clear. Okay, another question: are these simulation initial conditions independent? I mean, do different ICs produce the same galactic clusters? Answer is no. Different ICs will produce different galactic clusters and a different cosmic web. What one can say is that the initial conditions are taken to be a random realization of a particular choice of Gaussian random field. So Gaussian random field, remember, is defined by its power spectrum. So if I fix the power spectrum and I just randomly sample it once, and then I randomly sample it again, and I run two different simulations, one with the first one with the second initial conditions, I will get two cosmic webs which are different from each other when I visualize them. But if I calculate statistics on these two different cosmic webs, then within the noise, I will get the same statistics at the end. Okay. However, if I change the shape of the initial power spectrum and then I resample and set a new set of initial conditions, then the statistics of the final cosmic web will also be different. Okay, so for example, I may not have large scale modes, I may not have small scale modes, etc. I hope that answers the question. Is there anything else? Let me quickly check the Google Sheet. Okay, there's nothing in the Google Sheet. All right. So I don't see any other questions. So in that case, thank you all very much for your attention, and I will now.